Hey stats, you guys should all have a chapter 4 review. If you do not, it's posted on Google Classroom that you can print out. Or look at, and you can write it down on another sheet of paper, whatever you choose to do. I'm going to go through these problems with you, and then I'll probably post throughout this video some questions for you guys to answer on your own. So just jump right into it. Number one, the following table contains data from a study of 2 airlines which fly to small town USA. If one flight is selected, what's the probability of that one flight being both on time and from Upstate Airlines, okay? So normally I say and is the word that tells you that you are multiplying, except we're only choosing one flight, okay? So what I'm doing for this table as I'm looking at that one flight and the places where those two things intersect. So on time and Upstate Airlines. Upstate Airlines is this bottom right here, and number of flights on time would be here. So I'm looking at this 43 right here. That's where they cross each other. So on time and from Upstate Airlines was the 43 out of a total of, we have to figure out what the total number is. So number of flights on time, if I total these up, that would be 76. If I total these up, that would be 11. So there is a combined total of 87 flights. So 43 out of 87 are from are on time and from Upstate Airlines, okay? And you can convert that to a decimal if you want to. I'm just going to leave it as 43 over 87. Number 2, a firm uses trend projection and seasonal factors to simulate sales for a given time period. It assigns a 0 if sales fall, a 1 if sales are steady, 2 if sales rise moderately, and 3 if sales rise a lot. The simulator generates the following output, okay? I went ahead and counted these up for us. There are 31 simulations of these numbers run. So there's 31 numbers listed there. Estimate the probability that sales will rise at least moderately. Okay, so at least moderately. If sales fall, that's not at least moderately. If sales are steady, that's not at least moderately. At least moderately would be the 2s and the 3s, because if sales rise a lot, then that means it's still at least moderately. So I'm looking for the 2s and the 3s in this simulation. So there's a 2 here, a 2 here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 31. Let me see if I counted that up right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 31. And you can convert that to a decimal if you want to, but I'm just going to leave it as 16 over 31. That is my chances that sales are going to rise at least moderately. So about 50%, a little less than 50%. Okay, refer to the table which summarizes the results of disease versus no disease and positive negative. So this is have disease, this is does not have disease, positive results, negative results, okay? So things that should happen, if you have the disease, you should test positive. If you do not have the disease, you should test negative. These people here and these people here are getting false positives and false negatives. All right, so if one of the results is randomly selected, what is the probability that a false negative occurs? So a test indicates the person does not have the disease when in fact they do. Okay, so what is the probability of a false negative? That would be, all right, what does the probability suggest about the accuracy of the test? So getting a false negative would be like the probability of getting a, what is it, a negative given they have the disease. That's another way of writing a false negative. A negative given the fact that they have the disease. So here, when we're doing this, we're looking for how many people have the disease, and that's going to be my bottom number. So have the disease is these people up at the top of here, and that's going to be, what, 115? And negative results would be 4 out of 115. If I convert that to a decimal, that's less than 4%. 4 divided by 115 is 3.5% approximately. So 3.5% of the people who have the disease will test negative for it, which is unfortunate because those people are going to not get the treatment that they need. So what does this probability suggest about the accuracy of the test? We probably need to get a different test or test run the test twice, okay? So not good accuracy of that test, all right? Flip a coin twice, create the sample space of the possible outcomes. So when you flip a coin, you can get heads and tails, but if you flip it twice, you could get a head-head, a head-tail, a tail-head, or a tail-tail. That's the list of your sample spaces, okay? Number 5, swinging Sammy scores batting prowess was simulated to get an estimate of the probability that he will get a hit or a miss. So let 1 be a hit and 0 be an out. The output from the simulation was as follows: estimate the probability that he gets a hit. So this is going to be kind of similar to number 2. Again, we're counting the number 1s because we want to get a hit. There are, I think I counted these up, 42 total numbers here. So getting a hit, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 out of 42, which is 10 over 21, which is a little less than 50% of the time. 10 divided by 21 is 47.6%. So 47.6% of the time he's going to get a hit. Okay, number 6, in a certain class of students, there are 11 boys from, I'm going to say 11 boys from Wilmette, 7 girls from Wilmette, 5 boys from, Winnetka, 4 girls from Winnetka, 4 boys from Glencoe, and 4 girls from Glencoe. Okay. So I'm listing those off to the side. If a teacher calls upon a student to answer a question, what is the probability that the student will be a boy? Boys are here, here, here. So 11 plus 5 plus 4 is 20 boys total out of, girls would be 7, 4, and 4. That's 15. So 20 plus 15 is 35. Let me check that again. 11, 5, and 4, that is 20. Girls, 15, yep, so 35. 20 out of 35, which if I divide by 5 is 4/7. I have a 4 out of 7 chance of getting a boy. All right, assuming that a study of 500 randomly selected airplane routes show that 482 arrive on time. So late, if 482 are arriving on time, how many are arriving late? 18 are arriving late. Select the correct interpretation of the probability of an airplane arriving late. So the probability of late would be 18 out of 500, which is about 3.6%. So 3.6% of all of my airlines are arriving late. Interpret an event as significant if the probability is less than or equal to 0.05. Okay, so how do we interpret this if we have 3.6% of our airlines arriving late? Significant if it arrives less than or equal to 0.05. I'm trying to think of the words that we would use. It has it does not have a significant number of late planes, I would say, because it's less than or equal to 0.5. So, not a significant number of late planes, if that makes any sense at all. Because we're comparing it to 0.05, but that is actually 5%. So 3.6% were late. That is less than 5%, so not a significant number of late planes. Okay? I hope that made sense. Number 8, determine whether the events are disjoint. Disjoint means that they are unrelated. So like if we're looking at a Venn diagram, that means that we can't have anybody in the middle here. If they're disjoint, that means they're unrelated. I had to look this up. Read a book by Mark Twain and read a book about Tom Sawyer. The Adventures of Tom Sawyer or The Adventures of Huckleberry Finn, all of those involve the character Tom Sawyer, and they are all written by Mark Twain. So you can read a book that's by Mark Twain and a book about Tom Sawyer at the same time. Those books would fall in here. Okay, so it is not disjoint because we have books in here that are joined together that are about Tom Sawyer that are both written by Mark Twain. Okay, so not disjoint in that case. Evaluate the expression 8P4 and explain what it means. So let's type in 8P4 and let's see what we get. 8P4 is 1680. 1680 and explain what it means. So this is choosing 4 out of 8 when order matters. So maybe I'm selecting the top 4 runners out of 8 and I'm giving them first through fourth place. First place is not the same place as fourth place, so order matters in that case. Okay, number 10, a study conducted at a certain college shows that 65% of the school's graduates find a job in their chosen field within a year after graduation. Find the probability that 11 randomly selected graduates all find jobs. Okay, so I have 11 graduates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The chances that this one finds a job is 0.65 or 65%. The chances that this one finds a job is 65%. The chances that this one finds a job is 65%, 65%, 65%, etc., all the way through here. So how do I find the chances of all of them finding a job? I would take 65% and multiply it by itself 11 times, or take 65% to the 11th power, which is going to be crazy. 0.65 to the 11th power is 0.0088. So I have a 0.88% chance of all of them finding a job. Okay, so not a very good chance that all 11 of them are going to find a job, even though you have a 65% chance of finding a job. 11 of them the chances of all of them having a job at the end of the year will be really low. Round to the nearest thousandth if necessary. This is the nearest thousand. So 0.0088, that's my probability. All right, 11, express the indicated degree of likelihood as a probability value. Your mother could not have died 2 years before you were born. If we're talking about something that is impossible, that will not happen, the probability of something that will not ever happen has a probability of 0. So there is a 0% chance that your mother had died 2 years before you were born. There's a 0% chance of that happening. Okay, and I know you're going to get into the whole, well, what if you were adopted, blah, 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 then your mother could have died, whatever. You could not have died, your mother could not have died, your biological mother could not have died 2 years before you were born, because that's just the way that it works. All right. Number 12, refer to the table. We have positive results, negative results, have the disease, does not have the disease. These are different numbers than what we had before. What is the probability that the subject has the disease given, there's that given word, that the test result is negative? So probability of have given negative. I'm going to write that out. Okay. Now we're only looking at the negative people. That's going to be my bottom number. Negative result are all of these together. So 321 is going to be my bottom number because that's added together. Of those 321, how many have the disease? That would be 9. 9 out of 321. And I'm just going to leave it like that. I'm not going to reduce it or put it as a fraction. Okay. Of the 1232 people who came into the blood bank and gave blood, 397 people had high blood pressure. Estimate the probability that the next person comes in has high blood pressure. So we're just going to look at our past results. Our results in the past said that 397 out of 1232 have high blood pressure. So we're just going to use those numbers. 392 divided by 1232. So my next person has about a 31.8% chance of having high blood pressure, okay? Because we look on our past results, and that will tell us kind of approximately what the future results will look like, okay? Here's another contingency table or a this is like a 3x3 frequency table. If one of the 255 subjects, I'm going to put that down here in the corner, 255, if I add those all up, is randomly selected, find the probability in fractional form that the person is over 40 and drinks cola. Now, normally we say and means multiply, but we are only looking at one person. Find the probability that that one person is over 40 and drinks cola. So which number out of this table is over 40 and drinks cola? Over 40 drinks cola, that would be these 20 right here. That's where those two things cross each other. So I have 20 people that are over 40 and drink cola out of a total of 255. And that, oh, they just want us to leave it in fractional form. But I can divide both of those by 5. 40 divided by 5 is 4. 255 divided by 5 is 51. 51. 4 out of 51. That's my chances. Okay, moving on, number 15. In one town, 66% of adults have health insurance. What is the probability that 4 adults selected at random from the town all have health insurance? So we have 4 people. This is going to look like this example up here, number 10. So the first person, the chances of them having health insurance is 66%. Second person, 66%. Third person, 66%. Fourth person, 66%. So the chances of all of them having health insurance, I would multiply those together or take 0.66 to the 4th power. And the chances of all of them having health insurance is 18. We'll go 0.0 thousandth, so 4 decimal places, 0.1897. So I have an 18.97% that all 4 of those people have health insurance. Okay, number 16, if a person is randomly selected, find the probability that his or her birthday is not in May. The chances of being in May are 31 out of 365 because there are 31 days in May. So not May would be the opposite of that. 365 minus 31 is 334 out of 365, which is a 91.5%. So there's a 91.5% that the person I choose does not have a birthday in May. Okay, 17, compare probability and odds. Okay, probability is what you want over the total. Odds is what you want over what you don't want. Okay, so how can you create odds to probabilities? So let's say I want a heads when I flip a coin. The odds of getting a heads would be 1 to 1. Odds is getting ahead versus not getting ahead, 1 to 1. So if I want to convert that to a probability, what I want over what I don't want, those two are going to add up to be my total number. So 1 plus 1 is 2, and I have 1 out of 2 chance, right? Okay, so another example of that would be rolling a 3. I have a 1 to 5 odds of rolling a 3 because one side has a 3, 5 sides don't have a 3. Okay, if I add those two together, that gives me a total of 6 sides on the dice. So the probability of rolling a 3 is 1/6. Okay. 3 left, discuss the range of possible values for a probability. Give examples to support this. I'm not going to worry really about the examples, but the probabilities can only be numbers that are 0 to 1 as a decimal or 0% to 100%. Okay, you cannot have higher than 100% or lower than a 0% probability. Number 19, a statistics student plans to use a TI-84 plus calculator on her final exam. From past experience, she estimates there is a 0.92 probability that the calculator will work. So what's the chances that the calculator won't work before we go any further? That would be an 8% chance or a 0.08 that it's going to fail. Okay, she's going to bring 2 calculators to the exam. Okay, so let's find the probability of a fail and a fail. Let's find the probability that the calculator is going to fail both times. It has an 8% chance that it's going to fail the first time and an 8% chance that it's going to fail the second time. So 8% times 8%, 0.08 times 0.08. The chances of both of them failing is 0.0064. Okay, so less than 1% chance, this would be a 0.64% chance that it is going to fail both times. Use the probability that does she gain much by bringing a backup calculator? So if it has a 0.64% chance that it's going to fail, 100 minus 0.64 means that it has a 99.36% chance that I will have at least one of them working, right? 99.36. So I bump my 92% chance up to a 99.36% chance of at least having one working calculator. So I would say yes. That does give you, 7% more chance that I'm going to have a working calculator. Okay, if I bring two of them. Use the probability that she will be able to complete her exam with a working calculator. I have a 99.36% chance of having a working calculator by the end. So I would say it's worth it to bring two calculators. Last one. An author has 6 different books in print. If those 6 books are stacked in a random order, what is the probability that they are arranged in alphabetical order? So let's find the combination. I have 6 different books. Okay. This book could be any one of those 6 books. After that book is chosen, then I have 5 books that could be in the second spot, 4 books that could be in the third spot, 3 books that can be in the fourth spot, 2, and then 1. That is 6 factorial. If you do 6 factorial on your calculator, there are 720 different combinations. Okay, another way of doing this is doing 6p6. It's a permutation. You're selecting all of the books, but the order matters because it's going to look different if you stack them up in a different order. So 720 is the different combinations. What is the chances, or what's the probability of it being arranged in alphabetical order? That would be 1 over 720. Now, how does that change if I have 7 books instead of 6? That would be 7 factorial. So that is 5,040. So I have 1 out of 5,040 are the chances that they're arranged in alphabetical order if I do that randomly. Okay, so lots of stuff going on here. Sorry this video was a bit long, but there we go. Tomorrow, I don't think I'm going to have you guys test over Chapter 4, so this review is it. Tomorrow, I'm going to jump us right into Chapter 5 and start with 5.1.